Namaste, my friend, and welcome back to NEET Chemistry with Typical Monk. This is Class 7, the third and deepest chapter of bonding. Let me begin with a puzzle that troubled chemists for years. If you draw oxygen with Lewis dots, every electron pairs up neatly, and the molecule should feel nothing near a magnet. Yet, pour liquid oxygen between the poles of a magnet, and it clings there, suspended, refusing to fall. Lewis was wrong about oxygen. When Sarah first saw that experiment, she asked the perfect question: if the dots lie, what tells the truth? The answer is a beautiful idea called molecular orbital theory, and it also explains why water refuses to let go of itself. Today, one idea at a time, we go to the deepest layer of the bond. Take a slow breath. Let us begin. So what will you carry home from today's class? First, molecular orbital theory itself. How atomic orbitals combine into bonding and antibonding molecular orbitals that belong to the whole molecule. Second, bond order and magnetic behavior. How we measure the strength of a bond and why oxygen is paramagnetic when Lewis dots say it should not be. Third, dipole moment, polarity and Fajans rules. Why some molecules are polar and some cancel out. Fourth, hydrogen bonding, the quiet force between molecules and the difference between the inter and the intramolecular kind. And fifth, the NEET drills, assertion and reason, match the column, and a bond order numerical. So everything you learn today, you can also score with. Ready? One idea at a time. Let us start with why we need a whole new picture. In molecular orbital theory, the atomic orbitals of the two atoms do not just overlap in one spot, they merge and spread into new orbitals that belong to the entire molecule. These are the molecular orbitals, and the electrons now live in them, not on any single atom. And they come in two flavors. When orbitals add up in phase, they form a bonding orbital, lower in energy, which holds the atoms together. When they cancel out of phase, they form an antibonding orbital, higher in energy, marked with a star, which pushes the atoms apart. Every bond is a tug-of-war between these two. Now, the single most useful number in this chapter, the bond order. It is 1/2 of the bonding electrons minus the antibonding electrons. David likes to think of it as a scoreboard. Bonding electrons score for the bond, antibonding electrons score against it, and we have the difference. A higher bond order means a stronger, shorter bond. And here is the gift that Lewis could never give. Because molecular orbitals show us exactly which electrons are paired and which stand alone, they explain magnetism. A molecule with unpaired electrons is paramagnetic, drawn to a magnet, and that is precisely the secret of oxygen. Look at this diagram slowly, because it is the crown jewel of the whole theory, the molecular orbital diagram of oxygen. On each side sit the atomic orbitals of one oxygen atom. In the middle, the molecular orbitals they form, stacked by energy, low at the bottom, high at the top. First, we fill the electrons from the bottom up, lowest energy first, exactly as we do inside an atom. Oxygen brings 16 electrons in total, and we drop them in, level by level. Now watch the top. After the lower orbitals fill, the last two electrons reach the two pi star antibonding orbitals, which sit at equal energy. By Hund's rule, they go in singly, one in each, spins parallel before either can pair. And there it is, two unpaired electrons sitting alone in the pi star orbitals. That is exactly what makes oxygen paramagnetic, drawn to a magnet. Now this is the triumph of molecular orbital theory. It predicts what Lewis dots never could. Finally, count the bond order. Oxygen has 8 bonding electrons and 4 antibonding. 1/2 of 8 minus 4 is 2, a double bond. So oxygen has bond order 2, and yet carries 2 lonely, unpaired electrons. Now let us put that scoreboard to work across several species. Remember the rule: bond order is 1/2 of the bonding electrons minus the antibonding electrons. The higher it climbs, the stronger and shorter the bond, and the more stable the molecule. Look at nitrogen. It has a bond order of 3, a full triple bond. That triple bond is short, strong, and hard to break. And it is exactly why nitrogen gas is so unreactive that it fills most of the air you breathe. Now the clever part NEET loves. Take an electron away from oxygen and it leaves from an antibonding orbital, so it actually helps the bond. Oxygen plus the dioxygenyl ion ends up with bond order 2.5, stronger than neutral oxygen itself. Go the other way, add an electron into an antibonding orbital. The superoxide ion, oxygen minus, drops to bond order 1.5. Add 2 and peroxide, oxygen 2 minus, falls all the way to bond order 1. Antibonding electrons always weaken the bond. Let us work one full case out, loud, slowly, the monk's way, the bond order of the oxygen plus ion, the dioxygenyl ion. Start with what is given. Neutral oxygen carries 16 electrons. The plus sign means it has lost one, so oxygen plus has 15 electrons. Never rush past this count. Next, where does that electron leave from? Always from the highest occupied orbital, and in oxygen that is an antibonding pi star orbital. Losing an antibonding electron is good news for the bond. Now count the two teams. The bonding electrons stay at 8. The antibonding electrons were 4, and we removed 1, so now there are 3. Apply the rule. Bond order is 1/2 of 8 minus 3, which is 1/2 of 5, 2.5. And what does that mean? 2.5 is higher than oxygen's own bond order of 2. So the oxygen plus ion has a stronger and shorter bond than neutral oxygen. That single counterintuitive fact has been asked again and again. Lisa missed it once, then never again. Now we leave the inside of the molecule and step between molecules to a gentle force that shapes the world, the hydrogen bond. When hydrogen is bonded to a small, greedy atom, fluorine, oxygen, or nitrogen, the shared electrons are pulled so hard that the hydrogen is left almost bare and strongly positive. That naked hydrogen then reaches out to a lone pair on a neighboring atom, and a hydrogen bond forms. When these bonds form between separate molecules, we call them intermolecular, and they knit the molecules into a network. This is why water, hydrogen fluoride, and ammonia boil at surprisingly high temperatures. You must break all that hydrogen bonding before they can escape as gas. But hydrogen bonds can also fold inside a single molecule. Look at orthonitrophenol. Its hydroxyl group and its nitro group sit right next to each other. So the hydrogen bond closes up inside the one molecule. We call that intramolecular. Now compare it with paranitrophenol, where the two groups sit far apart on opposite ends. There, the hydrogen bond must reach across to other molecules. It is intermolecular, so paranitrophenol clings to its neighbors and is far less volatile. Ortho, locked up inside itself, escapes more easily. Orthonitrophenol is more volatile. Now sit up straight. These 5 lines are what NEET actually asks year after year. 1. Oxygen is paramagnetic because it holds 2 unpaired electrons in its pi star orbitals. This is the flagship result of molecular orbitals theory, expected in some form nearly every year. 2. Nitrogen has bond order 3, and for the oxygen family, 3. Carbon dioxide has 0 dipole moment because it is linear and symmetric, so its 2 bond dipoles cancel. But water is bent, so its dipoles do not cancel, and water is polar. Symmetry decides polarity, not the bonds alone. 4. Fajans rules. A small cation, a large anion, and a high charge all push an ionic bond toward more covalent character. 5. Hydrogen bonding is the reason water, hydrogen fluoride, and ammonia have such anomalously high boiling points for their size. Let us drill the NEET way. Remember the 4 options. Option A, both statements true and the reason explains the assertion. Option B, both true, but the reason does not explain the assertion. Option C, assertion true, reason false. Option D, assertion false, reason true. First one, assertion, the oxygen molecule is paramagnetic. Reason, it has 2 unpaired electrons in the pi star antibonding orbitals. Check each on its own. Is the assertion true? Yes, oxygen is paramagnetic. Is the reason true? Yes, 2 unpaired pi star electrons. And does the reason explain the assertion? Perfectly. The unpaired electrons are the very cause of the magnetism. Both true. Reason explains. Option A. Second one. Assertion. Carbon dioxide has zero dipole moment. Reason? The carbon-oxygen bonds in carbon dioxide are polar. Both statements are true. No doubt, the bonds truly are polar, and the molecule truly has zero dipole. But pause. Does the polarity of the bonds explain the zero dipole? No, the dipole is zero because the molecule is linear and symmetric, so the two equal bond dipoles point opposite and cancel. Both true, but the reason does not explain the assertion. Option B. This is the trap that catches John every time. Third one. Assertion. The bond order of the nitrogen molecule is 2. Reason. Nitrogen has a triple bond. Check the reason first. Yes, nitrogen has a triple bond. True. Now the assertion. A triple bond means bond order 3, not 2. So the assertion is false. Assertion false. Reason true. Option D. A quick match now. Say each answer aloud before I reveal it. Nitrogen. Bond order 3. A triple bond, short and unbreakable. The reason nitrogen fills the air. Oxygen. Bond order 2. A double bond, but with 2 unpaired electrons hiding inside. The dioxygenyl ion, oxygen plus, bond order 2.5. It lost an antibonding electron, so it is stronger than oxygen. And superoxide, oxygen minus, bond order 1.5. It gained an antibonding electron, so it is weaker. If all 4 came to you before the reveal, the scoreboard is becoming yours. Here is a favorite NEET format. I will read some statements. You silently count how many are correct. Statement 1. The oxygen molecule has 2 unpaired electrons. Hold your verdict. Statement 2. Antibonding electrons increase the bond order. Think about the scoreboard before you answer. Statement 3. Orthonitrophenol is more volatile than paranitrophenol. Picture where the 2 groups sit. So, how many are correct? 2 statements, the first and the third. Oxygen truly holds 2 unpaired electrons, and orthonitrophenol truly is more volatile because its hydrogen bond is locked inside itself. But the second one falls. Antibonding electrons subtract from the bond order. They never add to it. 2 correct. Statements 1 and 3. Now let me save you some marks. 2 myths that trap thousands of students every year. Myth 1. Removing an electron always weakens the bond. It feels so natural. Fewer electrons, weaker bond, surely? David believed this for months. But here is the truth. If the electron you remove comes from an antibonding orbital, the bond gets stronger, not weaker. That is exactly why the oxygen plus ion beats neutral oxygen with bond order 2.5 against 2. Always ask which orbital the electron leaves. Myth 2. Polar bonds always make a polar molecule. If the bonds are polar, the molecule must be polar, no? The truth. Symmetry can cancel the bond dipoles completely. Carbon dioxide has 2 polar bonds, yet it is linear and perfectly nonpolar. Its dipoles cancelling out. Now water has the same kind of polar bonds, but because it is bent, they do not cancel, and water is polar. Shape decides. Time to test yourself. Rapid fire. Here is the rule. I ask, you answer in your head before the reveal. No pen, no paper, just the ideas you built today. Question 1. What is the bond order of nitrogen? A triple bond, bond order 3. Question 2. Why is oxygen paramagnetic? Because it has 2 unpaired electrons in the pi star orbitals. Question 3. What is the bond order of the oxygen plus ion? It lost an antibonding electron, 2.5. Question 4. What is the dipole moment of carbon dioxide? Linear and symmetric. The dipole is 0. And question 5. The thinker. Which nitrophenol is more volatile? Ortho or para? Careful. Ortho locks its hydrogen bond inside one molecule so it does not cling to its neighbors. Ortho is more volatile. If you caught that, you have truly understood today's class. Let us gather the whole class in one slow breath. Atomic orbitals combine into molecular orbitals, bonding ones that hold atoms together and antibonding ones that push them apart. bond order is 1/2 of the bonding electrons minus the antibonding electrons. The higher it is, the stronger and shorter the bond. Oxygen is paramagnetic, with 2 unpaired electrons in its pi star orbitals, and nitrogen has bond order 3, a triple bond. Carbon dioxide is non-polar because its symmetry cancels the dipoles. Water is polar because it is bent, and Fajans rules tell us when an ionic bond turns covalent. And hydrogen bonding, from fluorine, oxygen, or nitrogen, explains the high boiling points of water, hydrogen fluoride, and ammonia. And it can be intramolecular, as in orthonitrophenol, or intermolecular, as in para. And next class, we open a new chapter, thermodynamics. We meet the first law and enthalpy, the accounting of energy in every reaction. Do not miss it. And so, my friend, we have reached the deepest layer of the bond. We saw why oxygen clings to a magnet, why nitrogen refuses to react, and why water holds so tightly to itself. This was the hardest stretch of the highest yield chapter in all of NEET Chemistry, and you have walked through it one idea at a time. Sarah, David, Lisa, and John all found these ideas hard at first, and all of them got there. Be patient with yourself. Tonight, draw the oxygen diagram once, slowly, from memory. One idea at a time, you will crack NEET, of this I am certain. If this class brought you clarity, subscribe to the channel so the next one finds you. Until then, keep going. I will see you in thermodynamics.